Today's video will look at the derivatives of log functions. Most of the time we'll work with the natural log function, but we'll look at logs of any base today as well. So an example of a log of any base would be like y equals log base a of x, where a could be any number. Now a would have to be positive, keep in mind. And an example of a natural log would be y equals natural log of x. Now, our derivative rule for any regular old log is 1 over x times natural log of the base. And we'll show you why that is. Let's say we had y equals log base a of x. We know with logs we can switch back and forth between log and exponential form. If we switch to exponential form, this becomes a to the y equals x. And this is something we have a derivative rule for. A to the y is just an exponential. So its derivative will be a to the y times ln of a. And then we need times a y prime, because we did a derivative with a y. And that's equal to 1. We'll get y prime by itself, and we'll have that it's equal to 1 over a to the y ln of a. Well, back up here, we know a to the y is just equal to x. So that tells us that y prime is just equal to 1 over x times natural log of a, which is exactly the formula we had up above. Now, if a was to equal e, so you had a base e, okay, natural log of e is just 1. So therefore, if we had started with y equals natural log of x, because that's really log base e, our derivative would just be 1 over x. And that's the one that we'll use most frequently. Okay, and here's just saying that, again, if your base is e, log base e of x, well, when you do that ln, or natural log of e, that just becomes a 1, giving you 1 over x for your derivative. Okay, and we will use this hundreds of times this year, so this is an important result. So, we know if it's just natural log of x, we'll get 1 over x. Well, we've got something other than x, so this is a chain rule. Here's our outside, here's our inside. So we'll just do our rule with our outside function, keeping the inside the same. So that means when we had 1 over x, we'll now have 1 over x cubed plus 1 times, because it's chain rule, derivative of the inside. So that's just 3x squared. If we neaten that up, notice we get y prime equals 3x squared over x cubed plus 1. Notice when we have it neatened up, this in the numerator is just the derivative of the inside. The denominator is just the inside. So when you have a chain rule case, it really just ends up as derivative of the inside in the numerator over your inside. So if you don't want to have to do chain rule, you can just think of it as that. Derivative of the inside over the inside. And that's what this is showing here. If you have natural log of g of x, the derivative will end up with the derivative of the inside on top, g prime of x, over the inside on the bottom. So taking that into account, natural log of sine x, our derivative, again, is the derivative of the inside over the inside. So we know sine x will be on bottom. Its derivative is just cos x. So we've got cos x over sine x. And if you wanted, we could even write that as cotangent x. Let's look at square root of natural log of x. So another way of thinking of this is natural log of x all raised to the 1/2. This is a chain rule case. It's important to identify that your outside is the thing being raised to the 1/2, and your inside is the natural log of x. So we do our derivative of the outside function first. Oops, this should be f of x. So we'll bring a 1/2 out front, keep the inside the same, now raised to the negative 1/2, times the derivative of the inside. Well, derivative of a natural log is just 1 over x. So you can leave it like this if you want, or the natural log raised to the negative 1/2, that'll come down to the bottom along with everything else. So you'll have 2x on the bottom and a square root of natural log of x. Either of those would be perfectly fine to leave it as. Okay, let's look at a chain rule example that deals with a base other than e. We'll do a log base 10. Keep in mind our rule is 1 over x natural log of a, where a is the base. So our derivative will equal 1 over, now x is when there's a plain old x in there, so we've got to put our inside where x is, times natural log of 10, times derivative of the inside. Well, derivative of the inside is just cos x. So you could leave it like this, or if you wanted, bring the cos x on top over everything. All right, we're going to look at a challenging example now, and we're going to show you 2 different ways that you could solve it. So first off, we've got natural log of x plus 1 over square root of x minus 2, all on the inside. So again, we'll do derivative of the inside over the inside. Now that might get a little messy, so it might be easier to write this as just the chain rule. So we know it's 1 over x in a normal case, so that means it's 1 over our inside times derivative of the inside. Well, we're going to have to do chain rule. So we'll do low d high minus high d low. Keep in mind, square root of x minus 2 is really x minus 2 to the 1/2. So we'll have 1/2 x minus 2 to the negative 1/2 all over low, low. Well, square root of x minus 2 squared will just give you x minus 2. So we'll work to neaten this up some. If you have 1 over a fraction, dividing by the fraction is the same as multiplying by the reciprocal. So this will just become square root of x minus 2 over x plus 1 times, we'll have a square root of x minus 2 minus, we'll have an x plus 1 on top and a 2 square root of x minus 2 in that denominator, all over x minus 2. Well, we're going to distribute that fraction out front through. So in the denominator, we'll just have an x plus 1 times an x minus 2. And in the numerator, we have to distribute through a square root of x minus 2. Well, square root of x minus 2 times square root of x minus 2 is just x minus 2. And then the square root of x minus 2 will cancel with the square root of x minus 2 in the bottom. So we'll have minus x plus 1 all over 2. We are now going to get a common denominator in the numerator there. So we'll put numerator and denominator over 2. So we'll now get 2x minus 4. We have to distribute the negative, giving us negative x minus 1 all over 2. And that's all over x plus 1, x minus 2. Now technically, if all it had wanted was the derivative, we could have stopped right here. But since we're going to do this a second way, I want to keep going and simplifying it just to show you that we'll get the same answer either way. When we neaten things up in our numerator, we'll end up with x minus 5 over 2, all divided by x plus 1 over x minus 2. Dividing by x plus 1 over x minus 2 is the same as multiplying by its reciprocal, which would be 1 over that. So therefore, the x plus 1 and the x minus 2 will just go down here with the 2. And this is our final derivative. Now, the other option is in the beginning. We could have used our log laws to simplify this a little. When you're dividing inside a log, that splits up into two separate logs where you're subtracting. So we could have done natural log of x plus 1 minus natural log of square root of x minus 2. And now take the derivative for this. So we'll do derivative of the inside over the inside. So we'll have 1 over x plus 1 minus, keep in mind this is x minus 2 to the 1/2. So derivative of the inside would be 1/2 x minus 2 to the negative 1/2 all over square root of x minus 2. Well, a negative exponent will bring this down to the bottom. So this is 1 over x plus 1 minus 1/2 over square root of x minus 2 times another square root of x minus 2. This will give us 1 over x plus 1 minus square root of x minus 2 times square root of x minus 2 is just x minus 2. And the 2 from the 1/2 will also come on the bottom. So now, just to show that it's the same thing, we'll get a common denominator. Over here, we have to multiply by 2 times x minus 2. Over here, we have to multiply by x plus 1. So on top, we'll get 2x minus 4. We'll get negative x minus 1 all over 2 times x minus 2 times x plus 1. And when you neaten that up, you'll get x minus 5 over 2 times x minus 2 times x plus 1. And that is exactly the same as we got once we simplified the other way. Now again, if it all it asks for is a derivative, you can just do the derivative and not simplify it. We just simplified it to show that you get the same thing no matter which method you use. So one last example to look at. Let's look at natural log of the absolute value of x. Well, remember, whenever we deal with absolute value of x, we need to think of it as a piecewise function. So f of x is really equal to regular old natural log of x if x is greater than 0. And it's equal to natural log of negative x if x is less than 0. Because if you have negative numbers, when you plug them in, the minus will make it a plus, just like the absolute value will. Now, the reason we don't have an equal to 0 is because you can't take a natural log of negatives or 0. So with the absolute value, putting a 0 in there, it would still be 0, and we can't have that. So when we take our derivative, we'll just take the derivative of the parts. Well, derivative of natural log we know is 1 over x, and that's if x is greater than 0. For the other part, derivative of the inside is negative 1 over negative x, which is really just 1 over x when x is less than 0. So, really, f prime of x is going to be equal to just 1 over x, provided x does not equal 0. And if you think of that, that makes sense because your domain is x greater than 0 for a log. So therefore, we couldn't have 0 as it anyway. Now, it's going to be helpful to remember that your natural log of absolute value of x is the same derivative as natural x's derivative, provided, again, x does not equal 0. So you could think of it as they're the same anywhere they are defined. That's all for today's video. We'll see you next class period.